Hello, welcome to GP Podcast. Right now, something profound is happening in the world of technology. Beneath the surface of our everyday lives, two absolutely colossal forces are quietly converging: artificial intelligence and quantum computing. And together, they are about to reshape our world in ways we are only just beginning to imagine. And look, this isn't some far-off science fiction dream. It's become an inevitability. You've got experts from every corner of the globe all agreeing that this monumental technological shift is already in motion. It's a kind of silent revolution, building momentum in labs and data centers all over the world. Its arrival isn't a matter of if, but when. And when seems to be getting closer and closer every single day. Just look at this number, $50 billion. That represents the staggering global investment from governments and corporations pouring into just one half of this equation. This is a new gold rush, a technological arms race for what many are calling quantum supremacy. So, to truly understand the revolution that's headed our way, we have to start with its first protagonist, quantum computing. And this isn't just about building faster computers. It's about a fundamentally new way of processing reality itself. The secret sauce here is the qubit. You see, our current computers use bits. They're either a 0 or a 1. Simple, reliable. But a qubit leverages the really strange laws of quantum mechanics to be a 0, a 1, or both at the exact same time. This bizarre property is called superposition, and it's what gives quantum computers their almost unbelievable power. I really love this analogy because it makes this tricky idea so easy to grasp. Think of a classical bit like a standard light switch. It's either on or it's off. That's it. A qubit, on the other hand, is like a dimmer switch. It can be fully on, fully off, and every single shade of brightness in between, all at once. By holding all these values at the same time, just a handful of qubits can explore a massive number of possibilities in parallel, completely blowing past the limits of even our most powerful supercomputers. But there's a catch, and it is a big one. This incredible power comes at a cost: fragility. Qubits are exquisitely delicate. I mean, the slightest vibration, a tiny change in temperature, any little bit of electromagnetic noise from the outside world can cause them to lose their special quantum state. This is a phenomenon called decoherence, and for years, this has been the massive wall holding quantum computing back. So that raises the critical question, doesn't it? How do you tame all this quantum chaos? How can you possibly build a stable machine out of something so inherently unstable? Well, the answer, it turns out, lies with the second protagonist of our story: artificial intelligence. So let me introduce you to Alpha Qubit. This was developed by Google's DeepMind, and it's not just any AI. It's a system that was designed for one specific purpose: to listen to the chaotic noise of a quantum processor. It actually learns the unique noise fingerprint of the hardware and can predict and correct errors before they ever have a chance to mess up a calculation. It's like giving the quantum computer an AI copilot that keeps it flying straight. And the results were just staggering. On Google's Willow quantum processor, Alpha Qubit managed to get a 30% reduction in errors. Now, this is a monumental achievement. It proved for the very first time that an AI-managed quantum system can actually become more stable as it gets bigger, which completely flips the biggest challenge of the last decade right on its head. Okay, let's move to our second protagonist and see how this all connects. Because while one AI was learning to control the quantum realm, a totally different branch of AI was learning to understand our physical world. This is all about AI evolving beyond just processing text and images on the internet. It's about AI getting a body. This is what's known as embodied AI, or physical AI. The whole goal is to create systems that can perceive the world through sensors, reason about what they're seeing, and then actually act on it, using things like robots, drones, or self-driving cars. But there's a problem. The internet has basically run out of data to teach this. To learn about physics, an AI needs to experience physics. So how does it learn? Well, it creates its own data. It's this brilliant process called a synthetic data pipeline. Developers start by capturing a small set of human demonstrations. The AI then uses those examples to generate a massive library of its own synthetic movements. Finally, it gets to practice those movements over and over again in these hyper-realistic virtual worlds, learning from trial and error millions of times faster than a physical robot ever could. And of course, building this kind of AI requires a whole new generation of architectures. We're moving way beyond models that just predict the next word in a sentence. As you can see from some of the names on this slide, the new goal is to build systems that can truly understand causality, simulate physics, and create an internal model of reality. This is the bedrock for an AI that can actually interact with our world. And now, here is where our two stories collide. We have an AI that can stabilize quantum computers, and we have quantum computers that will one day have the power to train the next vastly more complex generation of AI. It's a virtuous cycle, a powerful feedback loop where each technology pushes the other one forward, faster and faster. And you can bet the race to build these machines is heating up. As you can see, the tech giants are all taking different paths. PsiQuantum is betting on qubits made of light, which are naturally less prone to interference. Google is sticking with its high-speed superconducting qubits, but now supercharged by AI. And then you have Microsoft, pursuing this really experimental path with topological qubits, which are theoretically far more stable by their very nature. Of course, the road ahead isn't perfectly smooth. There are some major hurdles. We're facing a massive shortage of quantum engineers and physicists. We're needing to literally invent new kinds of hardware. We also have to urgently upgrade our digital security to what's called post-quantum cryptography, because a powerful quantum computer could break most of the encryption we use today. And of course, there are profound ethical questions we absolutely have to confront. So what does all of this mean for us, right now? What does this convergence actually look like in the very near future? Well, let's talk about 2026. The year many experts believe we're going to see the dawn of what's called industrial quantum advantage. This isn't about quantum computers on our desks. It's about solving huge, specific problems that are impossible for us today. In pharmaceuticals, it means simulating molecules to design new life-saving drugs in a fraction of the time. In material science, it means creating brand new compounds for better batteries or superconductors. And in finance, it's about perfectly optimizing investment portfolios and modeling incredibly complex risks. These are the areas where we'll feel the first massive economic impact. And that brings us to the timeline. Sometime between 2026 and 2029, we expect to see the very first instances of a quantum computer solving a real-world business problem better, faster, or cheaper than any classical supercomputer. That's the starting gun. From there, the impact will spread through the 2030s, and it's expected to lead to broad societal transformation in the 2040s. But that first milestone, that's just around the corner. So, we're left with this. A new era isn't coming, it's being built in labs as we speak. The convergence of AI and quantum computing isn't a matter of if, but how soon. The question is no longer about the technology. The question is about us. Are we ready for what comes next? That's all for this explainer. If you like the video, subscribe, leave a like, comment on what you liked most, and share the video. Thanks for watching.